Okay, in the last screencast, we talked about Young's double slit experiment. In this screencast, I'm going to try to explain qualitatively and quantitatively some more about this phenomena of light behaving like a wave. If you remember in that screencast, we had light rays that are striking a slide with two slits in it. And so there's two rectangular slits. And if light is in fact a wave, it's going to come through here and it's going to create some areas of interference where it's either bright or dark. And we're going to try to explain that in a little more detail here so that you understand why it would do that. And we'll get into wave interference, and then we'll quantitatively develop a mathematical relationship that'll explain how we can kind of predict where those bright and dark spots are going to be. First, I'm going to have you watch a video. Again, I would do this in class if we weren't distance learning, but if we're distance learning, the best I can do is show you a video of what I would do in class. So this here is a video, and what I'm going to do is get it playing, and it's going to show you a actual double slit on a screen using a common, construction quality laser.
Okay, so I'm going to try and demonstrate to you a practical experiment called Young's double slits, named after a bloke called Young who did loads of really cool physics. And this experiment uses two slits, as the name suggests. And this is really an amazing experiment, and you've got to do it yourself to really appreciate it. But I want to take you through it with this video first. If you're in my class, then you're going to do it next lesson yourself. We've got enough for you to do this experiment in pairs. So what does it involve? It involves this, which is a spirit level that's got a laser in it. So if I point that at the wall there, hopefully you can see it's a red laser. It's a nice low power laser that's going to be safe for us to use. Young did this hundreds of years ago, so he didn't have lasers, but they make our life easier, as you will see. We've got this thing here, which is a collection of double slits. So if you look really closely, you can probably see 4 slits in this slide. If I hold it up to maybe a white background, you see it more clearly. Each of those things that you can see there, oh no, that's lovely, that's focused really nicely. So you can see that each of those things that look like one slit is actually a pair of slits. And the ones on the right are quite far apart, and the ones on the left are really close together. So these are double slits. What happens when the light passes through these two slits is that it spreads out. So when light passes through a narrow gap, it spreads out, it diffracts. And then the light coming from each of those two slits can interfere. So I'm going to shine the laser light through. I'm going to use the leftmost pair of slits because that's going to work best. So I'm going to shine this laser through a double slit, and then all the way over there, I'm not sure if you can see it, is a screen. It's a long way away, and you'll find out why that is shortly. So, here we go. I'm going to turn the lights off. I'm going to turn the laser on, and I'm going to direct the laser through 2 of the slits. So the laser light is going through a double slit, 2 slits very close to each other. All the way down there on the screen, you might just see some red. Now, actually, let me show you what it looks like without the double slit. Without the double slit, it looks like a dot. Okay, let's go back. Now, I've put a double slit in the way. So the laser light is passing through both of those slits, it's spreading out, it's diffracting. But when it gets over here, you get this very interesting pattern of bright and dark fringes. So it goes bright, then dark, then bright, then dark, then bright, then dark, and so on. So this is a 2-slit interference pattern of light. Now if you're in my class, we've already done this.
Okay, so now you're probably wondering, why does he keep picking British professors? I don't know. They just seem to have the best presentations. But let's talk a little bit about this phenomena qualitatively on the next slide. So what you see is this bright and dark pattern up here. That's kind of what we saw. So basically, each one of those little tiny slits that I'm showing over here in the left top video, I should zoom in a little bit on that. Um, each one of those is acting like a source of waves. So basically, if you remember Huygens' principle, each point on this flat wavefront is its own source of a disturbance, a source of waves. So when one point passes through here, then you've got that single point, like it's a single source of wave, like that little in the ripple tank, that one arm with the ball on the end just touching the water. And then here on the other side, another point on that flat wavefront acts like a wave source. That's like the other arm with the little ball on the end tapping the surface of the water. So you've got this exact same phenomena as you saw in the ripple tank, where these two wave sources are going off into to the right. They're moving to the right. Well, those two wave sources are going to interfere. So you're going to have crests and troughs that are interfering. Excuse me. So when you get two wave crests, here's a wave crest coming from this source over here, interfering with a wave crest from this source over here. At the point where the two crests intersect, you're going to get a double high wave crest. So that's going to be a bright point of light as those things propagate over here, and as those things propagate over here, and of course right in the middle, you're going to have a bright light. So you get these bright areas where those two waves both strike that point on the screen at the same time. So the highest intensity light striking the same location at the same time, they amplify the intensity. That's called constructive interference. So you get a bright spot wherever the two crests cross over and meet at the same point. How about when a crest and a trough cross over? So when you get an overlap of a crest and a trough, and by the way, these are right from your text. Let's say you get a crest and a trough that meet on the screen. So you've got dark areas here. Notice how this is a crest right here coming from this source. Meanwhile, the in between these two, I'm looking in between. Let me do a different color here. In between, maybe green is better. These two wave fronts, in the middle there is going to be the lowest point, which would be a trough. So the lines represent the crests. The space exactly halfway between those two wave fronts is a trough. So moving over here, that point would be directly in between two wave crests, where it touches that red crest coming from this source over here. I've got a trough, and that's going to completely cancel out the to this point right here. It's going to completely cancel out the crest. The crest and the trough will add up to no intensity at all. So when that propagates to the right and it touches the screen right here, you're going to get a dark spot. And of course, you continually get crests hitting that spot and troughs hitting that same spot. So it's not going to go bright to dark. It's just going to stay dark, and these points will just stay bright. So here's some notes you might want to write down. I'll just walk through it. The interference pattern of dark and bright bands produced by light passing through two closely spaced. Those were very closely spaced, and we should say something about that. The spacing of those slits has to be very, very small to create this effect. If you didn't have very small spacing between those slits, with light which has a very tiny wavelength, you will just see two spots, two rectangles like we would expect to see. So it's only when that spacing gets really narrow do you see this effect of Young's double slit experiment. It can be explained by the addition or superposition of circular wavelets. That's what they call those little tiny sources of waves coming off to the right of the slide. The length of the path that each wave travels to a particular spot on the screen determines the phase of the wave at that location. The phase of the wave, when two waves have exactly the same crest at the same time, they're considered in phase. So if I have one phase or one wave that looks like that, and another wave, oops, didn't do that so well, another wave that is like this, these two are in phase when they're like that. If I were to take one of these guys here and shift it over, let's see if I can choose one of them. I'm just going to draw another one. Those are in phase. These two would be out of phase, where the crests and the troughs line up. So where the crests and the troughs line up, those are 180 degrees out of phase. When the crests line up with the crests, the blue and the green, those are in phase. Okay? So basically an interference pattern, which is what you're seeing on that screen, the bright and the dark fringes, we call them, can explain using the idea of interference of wavelets. So those tiny little sources of waves are interference, or interfering. Constructive interference occurs when the crests from the wavelets overlap, so you get double-sized crests. And destructive interference means that no light is present, so they're perfectly out of phase and they cancel each other out. I kind of went through that in the previous slide, so I'm not going to go through that again on this slide. So now we're going to get into a quantitative analysis of this. We're going to try to develop a mathematical expression that kind of lets us understand where those bright spots and dark spots are going to occur based on some parameters of the laser and the positioning of the slit, little double slit versus where the screen is located. So you can imagine, if you look here, if I've got a monochromatic source of light, okay, so I've got a monochromatic source of light. What that means, it's a single color. That's what the chromatic means. But as you know, colors are associated with wavelengths. So a single color means the same wavelength or a constant wavelength. So in our classroom, we actually have a laser, a red helium neon laser that has a wavelength of 632 nanometers. That little n is the nano. So when you've got the red laser that is incident upon the slits, these two sources each have exactly the same wavelength, 632 nanometers, because they come from a monochromatic laser right here. So it's like these two sources have exactly the same wavelength and the same, it's also called, they are coherent, which means in phase. So the word coherent, when it's applied to light, means that the source of the light is in phase, which these two crests will be exactly in phase with each other, as I demonstrated on the previous slide. So you can imagine when this particular guy hits the screen right there, that source, and this source hits the screen over here, they've traveled exactly the same distance. This is a point that's perfectly in the middle of those two slits. So if you drew a line through here, that point on the screen is exactly in the middle of those two slits. So the distance from this slit and this slit to that point in the middle is the same. So if they were in phase when they left here, they're going to be in phase when they arrive over here on the screen. So the crests are going to arrive at the same point and you're going to get a bright spot. Well, what about if, I'm going to scale this down a little bit, what about if you have over here where it's a different distance? So instead of having a point in the middle, I've got a point over here to the side. So I've got a different distance for those two sources to travel, those two wavelets. The crests on those two wavelets are traveling different distances. So let's call this one S1, let's call this one S2. S2 is longer, what if the difference between the two distances is exactly equal to a wavelength? Again, the difference between the distances that those two waves travel is exactly equal to one wavelength. So you can see this guy right here has to travel a little extra distance. And if that extra distance is exactly equal to one wavelength, then you're still going to have constructive interference at this point right here. If it's anything but a multiple of wavelengths, you're not going to get a bright spot there. In fact, if it's different by a half a wavelength, as you can imagine, you're going to get a trough at this source right here. If the difference is a half a wavelength, then a trough is going to arrive on the green line when you've got a crest from the blue line arriving at the same time. You're going to get a dark spot. So based on the different positions along this screen right here, the difference in the distances of the paths of the two sources is going to determine whether or not you get a bright spot or a dark spot. All right, let's look at that idea on a slide here that will allow us to see this in a little different way. So I've got two sources of light, basically those two little slits with wavelets coming out of each one. So you shine that laser on those two slits and they act as separate sources. And I've also got two different wavelengths or two different wave crests that I can kind of move around here, and they line up with the semicircular wavefronts there. So I've kind of scaled it to make that work out that way. So if you notice, what I'm going to do is I'm going to line up, see that point Y out there? That point Y is actually where two crests, two wavefronts are going to intersect. So what I can do is I can lay this right along there, and what I'm going to get rid of those two guys right there because that's just going to be distracting. But I'm going to lay down this so, or rotate it so the crest is right at the source, and then at point Y you can see I've got a crest right there. Okay, so I've got a crest at point Y, I've got a crest right here at the source. I'm going to take this other guy right here, that's coming out of source 2 now. So I'm going to line him up with, or this guy. I'm always using him. Sorry, girls. But here's source 2. There's a crest right there. And you notice how it's going to line up right at this point. Y again. Right here. So I've got two crests that line up. So if I had a screen that I placed right at that point, I'm going to have those two crests constantly hitting. And if it wasn't two crests, then it's going to be two troughs are going to hit at the same time. So it's just equal intensity. The intensity is not going to change. Whether it's a crest or a trough, its maximum amplitude is constantly going to be hitting at that point, whether it's on the top side of equilibrium or on the bottom side of equilibrium. You're going to have a high intensity point there. You're going to have a high intensity point here. There's going to be a point here that's dark because you can see that one of the wavefronts lines up directly in between two other wavefronts. So there's going to be a dark spot here. There's going to be a dark spot here. There's going to be a bright spot somewhere over here. So it's alternating dark and bright spots. Okay, picking up on where we just left off, I've moved this one wave off to the side to get it out of the way, but I've also drawn some lines in here. So I'm going to try to develop a mathematical expression that'll make sense to you. And I've shown the distance of the source 1 to a point on the screen Y using S1, and the distance from source 2 in blue, and the difference between those is exactly one wavelength. So when I zoom in on this, you can see the difference is exactly equal to a wavelength. Right here, there's an angle theta that makes between this line that's perpendicular to that point right there. So I've created a right triangle basically. So if you remember your trig, the distance between those two slits is D. Is that guy right there. So that's the hypotenuse of this little mini right triangle in here. So if I say the sine, sorry about that, the sine of that angle theta is equal to the opposite leg of that triangle, which is the wavelength divided by the hypotenuse, which is the distance between the slits. So the sine of the angle gives me this relationship right here, which is really important. And keep in mind, the difference between the two lengths doesn't have to be exactly one wavelength. It could be a multiple. Sorry about that. It could be a multiple of wavelengths. So this could be 2 wavelengths or 3 wavelengths difference as long as it's a multiple of wavelengths. So we tend to put m where m is any integer. So I could write this as sine of theta equals m lambda over d, and when m is 1, it's exactly 1 wavelength difference. Two wavelengths, okay? So that's the first step in quantitatively understanding this. Okay, I added a couple more lines here. I hope it doesn't get too confusing, but we're going to finish this up right now. Okay, so I've added this line right here, the distance between the midpoint between the slits and the screen. We'll call that L. So that's how far away the screen is from the slide with the 2 slits in it. Then this is a line right here, this other green one that I'm kind of highlighting in red right there. That's kind of another line from the midpoint to that point Y on the screen. And this angle turns out to be theta. It's exactly the same angle as you had down here in the small triangle. And this distance across the top to that bright fringe, that where the 2 peaks hit, we're going to call that Y. So we have another big triangle, the big green one that I just added. So if you think about tangent of that angle theta, that's going to be the opposite Y over the adjacent L. And tan theta is, these are really small angles. Keep in mind that guy's screen, how far away that screen was from where the laser was in the experiment that you saw in the video. And for that really long distance L, when L is real big, and the distance between the two, the center line and the first bright fringe, for instance, this distance Y might be only a couple millimeters. That's a super small angle. We're talking tenths or hundredths of a degree. For those small angles, so let me shrink this down a little bit. For small angles, tan theta and sine theta are basically equal. If you look on a trig table, I'm going to say approximately equal, sorry. Is approximately equal to, for small angles. Sorry about that. They're approximately equal. So that's kind of convenient, because what I'm going to do now is I'm going to set sine theta equal to tan theta. So if they're approximately equal for small angles, and I'm talking about angles about less than 15 degrees, which the angles that we're talking about for this particular experiment are on the order of maybe 2 degrees at the most. That means that m lambda over d is going to be equal to y over L. Take that on to the next slide. That's m lambda over d is equal to y over L. That's Young's equation for the double slit experiment. So all these variables, again, just to highlight what's what here, that's the distance between the slits. Okay, I took all that writing offline, so you didn't need to sit and watch me write, but here's what all those variables mean. I already mentioned the distance between the slits. D, wavelength of the light. So as you know, light comes in a lot of different wavelengths. Visible light between 400 to 700 nanometers. That's going to become important. The shorter wavelengths are the 400 nanometer ones. Those are violet. The 700 nanometer ones are the longer ones. Those are red. M is the order of the maxima. So the first order maxima is the brightest. That's when m equals 1, and the difference between the slits is 1 wavelength. Actually, the brightest is the 0th. So m could be anywhere from 0, any integer number, multiple of that. So when m is 0, that means the distance between the two wavelengths, between the two sources, is exactly the same. That'd be right in the middle. Y over here, that's the distance between the maxima on the screen. So the first order maxima, the second, the third, that's the first bright spot, the second, and the third. The distance between those is y. And then L is the distance of the screen from the slits. That's that long distance in that video between the screen and the slits themselves. I got to emphasize one more time that you can only use the approximation of tan theta approximately equal to sine theta for small angles. It's called the small angle approximation. So if you get angles larger than 15 degrees, then you have to separate out the two equations, solve for theta in the one that you know, substitute that theta into the other one from the previous slide. I know this was a long screencast. I hope it was helpful, and you can ask questions during the office hours on Tuesdays and Thursdays. Thanks, guys.